Okay, so this is our week 10, so it's next week. Yeah, I would like to very briefly go through what we learned in this quarter, and then go through some important concepts that I think might be present in exam. Also, just feel free to stop me whenever you want, and yeah. So, by the way, any questions about like general stuff, the exam or whatever? Okay. Yeah. Okay. So if no, let's start. First, just a very brief summary of what we learned in this quarter. So basically, there are like three important topics. The first topic we learned is the symmetry, right? So within the symmetry, we talk about spherical tensors. There's a one theorem related to the spherical tensor is the Wigner-Eckert theorem, right? Then we talk about some discrete symmetries. Basically, the parity, which actually very important. It will always give us some selection rules in the kind of a transition induced by some external perturbations. I will talk about this later. And another thing is the lattice translation, right? It's kind of important in solid state. There's one theorem, Bloch theorem. This theorem and also this theorem are all results from the group theory. And another discrete symmetry is a time reversal, right? How we function or how operator transform under the time reversal. That's what you need to know. So another big topic is the approximation method. So there are several subsections, subtopics, time independent, perturbation, right? So there are two cases. One is non-degenerate. There's just a formula you can just plug in and calculate the energy correction and wave function correction, stuff like that. And also another case is a degenerate case. There are also formulas, and we will talk about this later. And then it's time dependent perturbation. The general question we ask is like we have some original Hamiltonian H0, and we have some external drive, which is a Vt as a function of t. It's like this is the original energy levels. And assuming, for example, we initialize our state in some state n, And we would like to say what's the transition amplitude from N to another state I, right? That's the general question we want to ask. And in general, we would go to the interaction picture and calculate the time, this kind of evolution operator in the interaction picture, and we have the so-called Dyson series, and yeah, Fermi golden rule, stuff like that. And another thing is we learned is the variational method. So in this case, a trial function usually is given as a function of lambda, some parameter we eventually need to determine, right? We usually just calculate this energy average, by definition, it's like this. If this trial function is not normalized, then we need to normalize it here, and then just minimize our energy. We get the lambda we want, and then plug in. We get our approximate ground state energy. That's approximation part. Another part is the scattering, right? Like what we went through last week. There are two big topics. One is the Born approximation. And another method is the partial wave. Approximation. Basically, when your potential only depends on the magnitude of the R instead of the, there's no basically, okay, this Hamiltonian commute with this guy, and yeah, I think last week you learned, or this week you learned Berry phase, geometric phase. I don't think that will be in your exam. So I would focus on those three topics. Any questions so far? Okay, so this is just a very brief summary of what you learned this quarter. Of course, there are many details I didn't mention.
All right, Deem is in charge.
Sorry, I think I just lost my connection. Can you hear me now?
Yep.
Yes.
Okay, sorry about that. Okay. From where I lost my connection?
You said the Born approximation, and you wrote down the Hamiltonian commutation relations, then you cut out.
Okay, that's good.
Yeah, it was only for a sec.
Okay. Yeah, I don't know what's wrong with this. Okay. Yeah, so next, let's go to some topics that I think important and maybe may present in the exam. So let's first look at the symmetry part. First thing is about the parity, right? So parity is important when your Hamiltonian commute with this parity operation basically means your potential is symmetric around some axis, right? In this case, all the eigenstates can be classified into two categories. Basically, one is odd parity states, and another one is the even parity states. Let's denote as odd and even. So they're all eigenstates, and the worst, they're all eigenstate of the Hamiltonian, and the worst is the eigenstate of the parity operator. But the difference is one is minus sign, and another one is a plus sign, right? Or in the real space, the odd parity state means it's an odd function of x, and even means even function of x. It's very easy to understand. What I want to point out is this kind of parity symmetric Hamiltonian usually give us some selection rules which can simplify our calculation in many cases. Let's look at an example. Okay, so let's write down some. Basically, when I say selection rule, I mean this guy is 0 if A is even under the parity operation. This guy is also 0 if A is odd under parity operation. Even though it looks very simple, but sometimes just save your time and simplify your life. I'll give you an example. The most familiar example for you guys, I guess, is a harmonic oscillator. So this example is really important. In many situations, it emerges very naturally. Of course, we know the potential is symmetric around this axis. Therefore, we must be able to classify our states using this kind of a odd parity and even parity. That's indeed true. We know the ground state is an even parity state, which is symmetric around the x-axis, and the first excited state is an odd and the even odd this. So according to this kind of selection rules, we know this guy must be 0, right? You don't need to do any calculation because x would change the sign under the parity operation, right? Meaning that the x acting on this ground state is an odd parity state. This guy is an even parity state, right? So odd parity state inner product with the even parity state is 0 because they are the eigenstate of this operator with different eigenvalues, right? Similarly, this guy is non-zero, right? Because now x squared is even under this parity operation. And also you can make the same argument for this kind of A dagger, P operator, stuff like that. Any question about this kind of parity part?
Could you just remind us by making it like a quick list about which of the standard, XP, LZ, L squared are even and which are odd?
Oh, basically, A, they're all odd, right? A, because A, I think it's a linear position, linear combination of X and P, and XP definitely odd under the parity operation, and yeah. Of course, for these specific problems, this A and A dagger, for example, if I have some state n and another state n, there are some AM and AN. Oh, let's use another neighbor. M and what's the neighbor? I. Let's use IJ. So this guy is non-zero only when J equal to I, right? Only when the number of A dagger equal to the number of A, then it's non-zero, right? And of course, in this case, when I equal to J, this guy is also even under the parity operation, meaning that this operator will not change the parity of this state n. And so we have a chance to get non-zero results. Yeah, more questions? Yeah, I think this is the most common problems that can present in exam are related to parity. Yeah, we may need to do some calculations. And another topic is time reversal. Okay, so one important statement related to the time reversal is if a Hamiltonian has time reversal symmetry and it's also a spin zero, meaning that there's no spin degrees of freedom and also no degeneracy. Yeah, for example, Hamiltonian, the harmonic oscillator, right? Again. Yeah, it's that appears everywhere. So, right, this is time reversal invariant Hamiltonian, and also is spin zero. There's no spin degrees of freedom, and also there's no degeneracy, right? And the statement is you can always choose your eigenstate to be real. I think we talked about this like in previous discussion, but I just refresh your memory about this. The argument, like the proof is also very simple. Basically, imagine I have some, I have some eigenstate psi n with energy En. Then this is what we know. Now we apply this time reversal operator on the whole equation. We have this. This is just a number, so it's like this. And because time reversal commute with a Hamiltonian, we have this guy, meaning that the time this wave function, time reversal operator acting on wave function just give us a complex conjugate in the real space representation. This guy also have the same energy, En, but according to our assumption, there is no degeneracy, meaning that this guy must equal to psi n. So it's real. Of course, from this example, we know that wave function is always real. If you look up some textbooks, the wave function of a harmonic oscillator. And just a side remark, related to the Barry phase you learned this week, I think. Right. You know the Barry phase. For example, we initialize our state at some energy eigenstate n, and then we adiabatically evolve this system. Then this system will kind of follow along this this line, and give us this will accumulate a so-called Barry phase, which is given by minus I 0 t e t prime. This guy, right? This is always real number. You can prove it very easily. I think yourself should already mention this in class. So if your set n is real, this guy, this Barry phase is always 0, meaning that we want some complex wave functions, meaning that we hope our system has no time reversal symmetry. And that's why we usually need some magnetic field or spin degrees freedom to have non-zero Barry phase. That's a side remark.
A question on the time reversal symmetry. So did you get this non-degeneracy by setting psi n to be real, or did you set psi n to be real and get the non-degeneracy?
No, non-degeneracy is an assumption.
Yeah. And the spin 0 is also an assumption, or
yes, also the assumption. Because only as I will talk about later. When your spin is 0, then we can say this time reversal acting on this wave function, just acting like a complex conjugate. If there's a spin, right, there's some rotation metrics. Right? It's more tricky.
Right.
Yeah. We only learn this kind of basics in class. Once you dig into some kind of a papers research, you would definitely need to know more about this.
So basically, you get that we can choose psi n to be real given those two assumptions in the time
exactly. Yes. Yeah. This is the input. Output is real. One example is like this: simple harmonic oscillator. Yeah. Another example is the free particles, right? The eigenstate is nothing but the plane wave. And you can say this is generally not real. This is because there's a degeneracy between p and minus p. But at a specific point, p equals 0, there's no degeneracy. And if you set p equals 0, this eigenstate becomes a real number. Right? Yeah, you can always come up with some simple examples to help you to understand this kind of a more abstract statement. Okay, so next question is how the wave function transform under the time reversal. So let's look at the spin 0 case, meaning that there's no spin degrees freedom. First, there are two representations we usually use. One is a real space representation in real space. Another one is in the momentum space, right? So in real space, one equation, like one statement you need to know is this time reversal acting on the cat x give it itself, basically acting on x trivially. This is what's so easy to say because we know classically with the time reversal, the position will remain the same, meaning that we want to preserve this good property at quantum level. That tells us this statement, right? X remains invariant under the time reversal operation. And now if we assume x equal to x, okay, so this is just the equation, meaning that this cat x is the eigencat of x operator. Now let's look at what is this guy. This guy is, we can do a trick. It's a very common trick we usually do in the quantum mechanics, right? Basically, this guy is 1, right? So doesn't matter. But look at this. This just x. And x acting on this state by definition is x. So it's x just a number. Then meaning that this time reversal operator acting on x also an eigenstate of operator x with eigenvalue x. So we can always choose this guy to be cat x. This is not the case for the momentum operator, as you will see. So once you have this equation, you know how the wave function transform under the time reversal in real space. Like this, right? Things. I just insert the identity. Identity, right? Remember, this guy is just a number. So under this operation, time reversal operation, it will give us the complex conjugate. But this time reversal operator acting on this cat x prime, just give us the x prime itself. Then we know we do a projection on the real space, onto the real space. We get this. So we say, okay, under a time reversal operation, our wave function in the real space just becomes a conjugate, complex conjugate of the original wave function. This is a very simple derivation. You can find it in any textbook, I'm pretty sure. One important example, I guess, is this guy, the spherical harmonics. So we know under the time reversal, we just take this complex conjugate. If you look at the expression of this concrete expression of this spherical harmonics, you will find this minus m. And this, of course, equivalent to write in this way. Time reversal acting on this cat give us right. Yeah, this is how wave function transform in the real space, which is very easy, just take a complex conjugate. And in the momentum space, the situation is a little bit different. This is because the momentum operator would flip the sign under the time reversal. this would imply the momentum, sorry, the time reversal operator acting on this cat p would give us the minus p. You can also prove this by yourself very easily, and very similar to what we did here. And then it's not difficult to imagine that under the time reversal, our original wave function would change to the complex conjugate and also with the momentum flipped. Right. Any question about this part? Okay, so this is how the wave function transform under the time reversal for the spin 0 case. For general spin J case, basically there's a spin degrees freedom we need to deal with, right? In this case, if you look up on the textbook, the time reversal would be able to written this way. K is just a complex conjugate. JY is the generator, you know, the generator corresponding to SU3 algebra. For spin J, we can always kind of find the representation of this JY. For example, for the spin 1/2 case, which is the most common example, like we often use because, you know, in all the electrons have spin 1/2, which is in this case. Basically, under this time reversal operation, your direction of spin flips. That's also makes sense. That's how we, that's why we define this time reversal in this way. You can check it by yourself. It's also in the Sakura textbook. Okay, so now you say you know how to.
I just have a quick question.
Sure.
So for that representation where it's in the y basis, that is only true if your wave function is in the z basis, correct?
Yeah, that's true. Yeah.
Okay.
That's true. Yeah. Yeah. Basically, yeah. The final goal, is kind of we want the spin flip under the time reversal. That's how that's how we define our time reversal operator. Okay, so yeah, so that's what I want to say about the symmetry part. Basically, it's the parity and some associated selection rules. Make some argument about the parity, even parity or odd parity. And then time reversal, basically one statement for the spin 0 case. And then you need to know how the wave function transform under the time reversal. The starting point of this kind of a transformation of wave function, as you can see, one is this guy. X should remain the same on the time reversal. That's also kind of how our intuition kind of is kind of agree with our intuition, right? And another is this guy. It's the momentum will flip the sign, and another thing is the spin will flip the sign. Everything kind of agrees with our intuition. Starting from this kind of basic equations, we can derive how the wave function transform. Okay, so the next thing I want to say is the approximation. So for the approximation for the non-degenerate case, you can look up on the textbook like the formulas. I don't want to waste my time on this. I'm pretty sure you know how to do it. There are many homework problems you can practice with. And for the degenerate case, instead of writing down the formula, let me give you a concrete example to show you how to kind of deal with it. I think it will be helpful. I just assuming all numbers are real numbers. I don't want to kind of bother with kind of complex conjugate or whatever. So AAB, this is the real Hamiltonian. Sorry, this is the original Hamiltonian H0 on perturbed. And another is the perturbed part. So the general procedure we usually do is the first, we need to diagonalize this small degenerate space, right? A epsilon epsilon A. Originally for H0, there's a degeneracy A corresponding to the cat 1 and cat 2. Let's call this 1, 2, 3. Of course, now if we include the perturbation epsilon physically corresponding to, it will introduce the hopping between those two states. Basically, we will have a hyperdize. They will hyperdize and get two non-degenerate states, which the separation usually is proportional to epsilon, the hopping amplitude, right? And the eigenstate is now, instead of 1 and 2, it's just some specific linear combination of 1, 2, and 1, 2, right? Then now, after this procedure, we have non-degenerate energy levels with some eigen cat. To get the second order approximation, the correction to the energy, we just apply the formula we have from the non-degenerate case. That's how we usually proceed, right? One special case is when epsilon equals 0, and there's a homework problem, right? And we also did that problem in the discussion long time ago. Basically, you need to construct some effective Hamiltonian in the subspace and diagonalize that effective Hamiltonian, you get the correction. And you can look up on the, you can kind of refresh your memory by looking at the homework problem. The solution is also on CCLE.
I have a question about this, sorry.
Sure.
So in that one, we ended up pretty much diagonalizing the projection of V squared. And then presumably if that still didn't have anything, you could go to V cubed, et cetera, et cetera. But at what point, what's the easy way to show that a certain perturbation won't lift to degeneracy if it won't?
What's perturbation? Okay, so for our case, I think the only chance the perturbation won't leave the degeneracy is when epsilon equal to 0. If epsilon is non-zero, you always get the energy like A plus epsilon and A minus epsilon, and you will have a splitting, which will.
Of course, right. But epsilon can equal 0 and still have the degeneracy be lifted.
Yeah.
So what would be? I mean, would delta 1 have to equal delta 2 in your image so that you could really? So there's no unique information between the two rows. How could you tell by looking at a perturbation that it won't lift a degeneracy?
Sorry, what do you mean by delta 1 and delta?
I mean, in your V matrix, you have delta 1 and delta 2.
So at the first order, we only look at the stays within the subspace, right? We don't need to worry about delta 1, delta 2. They are kind of hopping between the third level and the levels within the subspace. That's corresponding to higher order, right?
That's right. That's right. But I mean to any order. Like say the epsilons are 0, and then you go to the next order to see what the right diagonalization of the degeneracy is, and then you don't see anything there, and then you go to the next order, and then the next order. At what point can you call it quits and say the degeneracy will never be lifted by this perturbation?
No. Okay. So if they are 0, and then so how can you get if it's 0 at for example, if epsilon is 0, you want to do the second order. What I'm saying here is you cannot just naively apply the formula you have. That will give you the wrong answer because that assumes there's no degeneracy. And what we need to do is using this kind of approach to do it. This would generally give us a non-zero. At second order, if delta 1 and delta 2 are non-zero, this would generally remove the degeneracy. I'm not sure what's the question exactly you're asking.
Yeah, I'm just saying there are certain perturbations that don't lift certain degeneracies. It can happen. And I'm saying our whole construct here, we're really assuming that the perturbation will lift the degeneracy.
Right.
So we have all these tools for figuring out how it will lift the degeneracy.
Right.
And then the tools become really hard if you have to go to more orders. But my question is, because there are perturbations that just don't lift the degeneracy,
sure.
how do you tell?
Okay, I say you're asking a general question like when the perturbation, how do we know in general whether the perturbation leaves the degeneracy or not, right?
That's right. That's right.
So that's okay. So that's a very interesting problem. Basically, when you have some degeneracy, if it's not removed, meaning that there must be some robust kind of a thing protecting this. Usually, this is related to symmetry, and meaning that as long as the perturbation was obey that symmetry, for example, I don't know, parity operation, parity symmetry, as long as your perturbation obey the same symmetry that preserve, so that protect this degeneracy, then this degeneracy will not be removed. That's a very general statement, actually.
Okay, thank you.
Yeah. As you can say, for yeah, this is a very good question to ask. When we have some symmetries, as we learned in class, usually means there's some degeneracies. There are some specific points that the degeneracy is preserved, is protected by the symmetry. As long as the symmetry is there, the degeneracy is always there, meaning that no matter what perturbation I add, as long as the perturbation obey the same symmetry, the degeneracy is always there. That's called okay. So there are some it's called symmetry protect phases. Like when you look at some material, there's some phases that's associated with some symmetries, and we say okay, it's a robust. It's a topological phases, and that's because it's protected by some symmetry constraints. As long as the perturbation obey the same symmetry associated with the phase, of course, the phase is still there. It's robust. If you apply some perturbation that break the symmetry, then your original kind of a phase will break down, and you need to, it will, the system is driven to another phase. It's related to here, what you're asking here. Okay, so thanks for asking these questions. Okay, so another thing is the variational method. I also don't want to waste too much time on this. You know how to do it. If not, you should look at homework problems and learn how to do it. And another important thing is time-dependent perturbation theory. This is a very important. So first, we need to understand what's the kind of a setup we start with, right? It's like we have some original Hamiltonian. This is our system. It has some energy levels, 0, 1, and some n, some I don't know, I just draw it randomly. Now, imagine I initialize our system in the state I, and we drive our system with some perturbations. For example, we apply some oscillation electric field or magnetic field, and then ask the question that what's the probability that this system will find in this cat n after some time. This is the general question we want to ask. And of course, by the way, this is also called the transition amplitude. Right. The square of this guy gave us the transition probability from the I to N. This is not very convenient for computational purpose. We usually go to the interaction picture, and there's an equation relate this transition amplitude to a quantity that is easily can be calculated, which is there's some phase factor. We really don't care because the transition probability are the same. It's independent of this phase factor and this guy. This quantity is can be easily calculated, and it's because this is ui t naught equal to 1 minus I h bar divided by h bar t naught t I t prime. This is known as the Dyson series, right? And one can write down this guy. The first order is delta I ni, and the second order, sorry, the zeroth order, the first order is given by this. We usually stop at this first order unless it's 0. And this whole thing can be simplified to some expressions that can be easily evaluated. So as you can see, the transition amplitude, eventually to get this amplitude, we only need to do an integral, right? And of course, when you're there are many concepts related to these topics, like Fermi's golden rule and some formulas, but the starting point is what I'm saying here. Okay, so I think the time is up. So there's another topic is scattering. On scattering, but as we went through it in detail last week, so I'll stop here. And any questions, just if you have a questions, just stay here and we can discuss. If no, you're free to go. But eventually, I will upload my notes onto CCLE so you can take a look.
I also have a quick question regarding what to actually expect on this exam. Should we be focusing on these topics or just all of quantum? Because Professor Yaroslav sort of made it sound like all of quantum is on the table.
Okay, so I definitely you should focus on the topics now this course. And yeah, here I just pick out some important topics like from the pure exam point of view.
Mhm.
This is easy to give problems on, right?
Mhm.
Yeah, definitely there are many other important topics. For example, I didn't mention this kind of a spherical tensor and we're gonna echo the theorem. I would say it's quite difficult to give a good exam problem
Mhm.
about this topic, and it's important by itself, definitely. And yeah,
Just a quick question regarding the exam. How well should we know WKB just in case? Because it can be a huge topic if you're not careful, sort of.
I don't think there will be like a big program about WKB and yeah, but definitely need to. I think there's one homework problem. If you
Yeah.
know how to do it, then that's good.
Okay.
Okay, so a general statement I can make about final exam is if you know how to do the most of the homework problems, then you're definitely fine. So it should be similar to your homework problems. Not like the difficulty levels should kind of a similar or less, or we're not beyond that.
G, have you seen the test? Like, are you speaking from having looked at it?
Yeah.
Okay, that's good.
That is good because last time we were told the same thing and it definitely was not the case.
No, this time we simplified the exam and not. We even kind of
Okay.
we even remove one problem. Yeah.
Nice.
Oh my God. Wait, can you tell us how many there are or no?
I don't know whether I can tell you guys.
Okay, that's okay.
I think this time is should be much better compared with last year.
Okay.
Okay.